So now we're going to review some of the stuff about combinations that we've already done and extend it a little bit further. The main thing for combinations, as opposed to permutations, is that the order does not matter. So you have to make your decision. What are kinds of questions where the order doesn't matter? And so some typical ones are card games where you get a certain amount of cards and it doesn't matter what order those cards were given to you, such as poker. Or if you're making groups, right? If I'm making a group of 3 people in this class to present tomorrow, well, if I make a group of 3 and you say, I don't like that group, and then I say the same group in a different order, you're like, that's still the same group. Because the order doesn't matter. It doesn't change the group if we change the order of the people in the group. So we get, and this is supposed to, one thing in here, there's not supposed to be that line in there. We found out already that all a combination was a permutation where you divide out the order. So dividing by the extra r factorial divides out that order, and we get our formula for combinations. This formula is on your formula sheet as well. And here are some special cases. If you have n objects and you choose all n of them, there's only one way that that can be done, right? You have 4 prizes and you get to pick all 4. Ooh, which way should I do it? Well, you have to take all 4 of them. There's only one way to do that. If you have n objects and you choose one of them, so if I take a deck of 52 cards and I say you get to choose one card, how many ways can you do that? Well, 52 choose 1. There's going to be 52 different ways to do that. And this last one, what this is trying to say formulaically and with the outside numbers is that if you choose one card, every time you choose one card from a deck of 52, you are left with 51 cards left. So, although this seems like a much harder question, I have 52 cards. You get to choose 51 of them. How many ways can that be done if the order doesn't matter? All of a sudden your mind starts thinking this is a lot more complicated because you're like, okay, I could have all of those cards. But every time you choose 51, one of them is left out. And so 52 choose 51 is going to be equal to 52 choose 1, which there's just 52 ways. So if these two numbers add up to the number that you started with, they'll always be equal. And so here's an example of 10. If I have 10 cards and I choose 4, well, that's the same as if I had 10 cards and choose 6. Because every time I make a group of 4, I leave myself another group of 6. So now, how many poker hands are possible? Have you ever played poker? If there are 52 cards in a deck, you get 5 cards, and the order doesn't matter. The number of poker hands is just 52 choose 5. So if we go to our calculator, two, 5, 9, 8, 9, 6, 0. Almost 2.6 million poker hands. So if you watch, here we go, random cards. Card number 1. Card number 2. Card number 3, 4, and 5. I just randomly picked 5 cards. Look at this. 2 of spades, 5 of clubs, 4 of hearts, queen of spades, and the ace of clubs. Wow. probably live the rest of your life and never see this again. Because this one hand that I just pulled, I had a 1 in almost 2.6 million chance of getting this, so this must be special. But if you've played poker, this is less than mediocre. This is not a very good hand to have. But its chances, my chances of getting this right now, those exact 5 cards, are the same chance of getting any other exact 5 cards. It's just that this organization of them isn't that exciting. But the chances of getting that, since there's 2.6 million hands, and maybe that's what makes poker so fascinating, is all the different combinations of cards you could get. So when you're trying to figure out what your opponent has, you have to think about those kind of things. And we're going to do some counting of poker hands today. So groups, committees is another thing where the order doesn't matter. But sometimes our committees are broken up into smaller chunks. Like we want 2 boys and 3 girls on this committee. So this becomes a decisions question because you have 2 main decisions that need to be made. You have to figure out which boys you're going to pick, and you have to figure out which girls you have to pick. For our boys, there's 15 of them, and you want to choose 2 of them. So the order doesn't matter there. And then for your girls, you have 18 of them, and you want to choose 3 of them. What symbol am I going to put here in the middle between these? Multiplication or addition? Multiplication. Because there's 2 decisions. It's not a cases question, because 15 choose 2 just selects 2 boys, but it's not your whole committee that you've made. So multiply those together, go to your calculator, figure out those values, and write down the answer. So you have a group of students in a class, and you want to separate them into 3 groups. You want 8 students in group A, 5 students in group B, and 7 students in group C. How can this be done? Well, how many students do we have in total? 20. How many decisions do we have to make? There's 3 separate decisions here. Can you see that? You have to decide who's in group A, then decide who's in group B, and decide who's in group C.
Sorry for the interruption. Would Ms. Basario please contact the office? And would Callie Beal-Chase please report to the office for a message?
So let's say we decide to choose group A first. And then we'll talk about, does it matter which group that we choose first? If you choose group A first, how many ways can you choose 8 people to be in that group? What will I put in this first space? Something, choose 8. 20. Makes sense. There's 20 people. You choose 8 of them to be in group A. Then group B. You need 5 in group B. Yeah, now there's only 12 people left. So the number 1 mistake here is you do 20, choose 5. But you have to realize that once you've chosen 8 people to be in group A, they're already taken out. And then in group C, you need to choose 7 from 7, which is 1, which makes sense, because whoever's left, it's not like you're sitting in class, right? Group A gets chosen. You're like, oh, wonder what group I'm going to be in. Group B gets chosen. You're like, oh, I can't wait to find out what group I'm in. You're like, okay, everybody who's left is in group C. Oh, yeah. So multiply this out and see what you get. You get a big number. And then I want to see what would happen if you chose it in a different order. What happens if you chose group B first, then group A, then group C? Do you get the same number, or did it matter? It shouldn't matter, right? But try it. And once someone has a number, I'll put it up here. Now, I think you could have also figured this question out if I gave it to you 3 days ago. Now, if we went 3 days ago, we wouldn't have learned combinations yet. You wouldn't know how this C is, you wouldn't know it existed. So how could we solve this question using permutations only? Why? So we could make this like a Mississippi question. So in other words, if you lined up all your students from tallest to shortest, or whatever way from oldest to youngest, and then you took if you took that word and you said, how many arrangements are there of that word? And each unique arrangement then would get placed on your students in order, and then they'd find out, oh, I'm in group A, oh, I'm in group B, oh, I'm in group C. That should be the same amount. And if we did this as identical objects, well, that would be 20 factorial over repetition 8 factorial, 5 factorial, 7 factorial. And if we actually use our formulas up here, just do it underneath in a different color. 20 choose 8. That's 20 factorial, 8 factorial, and what would the other number be? 12, because the bottom two have to add up. And this one would be 12 factorial on top, 5 factorial, and the number on the bottom would be? 7. And this one would be 7 factorial on the top, 7 factorial on the bottom, and the other one would be? No, 7 plus 1 adds up to 8.
Sorry, last but not least, if we can please have
0 factor.
time 12 now of students, please head to the gym
If you were multiplying these, does it make sense that this cancels out?
Please contact the office.
7 factorial divided by 7 factorial. 0 factorial is 1, so I'm just going to put a line through it. So everything that cancels out is going to leave you with 1. Anything else cancel out? Oh, this 12 and this 12 would cancel out. And what are you left with? On top, the only thing is 20 factorial. On the bottom is 8, 5, and 7. So depending on how you logically think about the problem, there might be more than one strategy or solution to it, as is the case in this one. So we've already learned that there are 52 choose 5 poker hands in total. A number of those have clubs in them. So what would I have to do to count all the ways of not getting clubs? Because I want to count the number of poker hands with no clubs. How could I do that? Just hope you get lucky. Did I get a club? No, good. Oh, man, that didn't work. So you could spend all day just doing it randomly and hoping you don't get a club. Yes. Or the easier way to make sure that you don't get a club is to take your deck of cards, go through and go, oh, here's a club, take it out, take it out, take it out, and take out all 13 clubs. How many cards would you be left with then? 39. And then if you did 39 choose 5, each of those groups of 5, would they have any clubs? No. Would you have counted all of them? Yes. I think this is a really pretty number. I don't know. I think it looks pretty, right? Is it pretty?
Yeah.
What is it? What is it?
575,000.
Oh, Oh, nice. 5, 7, 5, 7, 5, 7. Thank you. Yeah. Okay, so there are the number of poker hands with no clubs. Part B, find the number of poker hands with at least one club. Okay? What I'm going to do as an experiment on this question right now is I'm going to become a salesperson. I'm going to try to sell you 3 solutions. I'm not going to tell you if all 3 solutions are right. I'm going to sell them to you as if they're right. All 3 might be wrong. 1 might be right, 2 might be right. That's what you have to decide. But I'm going to try to sell each of them to you as the right solution for figuring out the number of poker hands with at least 1 club. Okay. Number 1. Sales pitch number 1. Well, I just found out that I want at least 1 club. I'm going to say to myself, well, how could I do that to guarantee that I have at least 1 club? So I take out all 13 clubs and put them in a separate pile. And I go to those 13 cards and I choose one of them. That gives me at least 1 club. I then take the remaining 12 clubs that are left, I put them back in my deck of cards, I shuffle things up, and then I pick 4 more cards. So now I have, instead of 52 cards in that part, there's only 51 cards left. And I choose 4 more of them, which means I could get more clubs, but there's a possibility that I don't get any more clubs. But no matter what, since I've already made sure that I chose 1 club, I'm going to be guaranteed to have at least 1 club. Sales pitch number 1. Sales pitch number 2. Well, in part A, I figured out how many hands, that pretty number, 57, 57, 57, how many had no clubs. So I'm thinking, well, if I use the not strategy and I take all the poker hands possible, 52, choose 5, and I subtract the bad ones, which was 39, choose 5, whatever I get left would have to have at least 1 club. Sales pitch number 3. This one, I get nervous when I'm counting the not strategy, or the first one seems simple. I want to make sure I'm going to count things really long. I'm going to count it in cases. And in case 1, I'm going to count out how many hands have exactly 1 club. So I take my 13 clubs, I choose 1 of them, and then I take my other 39 cards that aren't clubs, and I choose 4 more, and that'll give me a poker hand of 5 cards with 1 club. Then I'll go to case 2. And I'll figure out how many poker hands have 2 clubs. So I take my 13 clubs, I now choose 2 of them, and from my 39 other cards, I choose 3 more. That will give me 2 clubs. I'm going to do this all the way. Case 3 is going to be 3 clubs. So 13, choose 3, and 39, choose 2, and case 4 would be 4 clubs. 13, choose 4, and 39, choose 1. And finally, case 5, I happen to get all 5 clubs, so I just have to do 13, choose 5. If I take all of those cases of exactly 1 club, exactly 2 clubs, exactly 3, exactly 4, exactly 5, and I add them together, I'll be guaranteed to get at least 1 club. Now it's your turn to think. Are all 3 of these good methods? Or have I made up stuff and all three of these don't work? Would the teacher do that to you? So here's our results after calculations, and our results now show that all three can't be right because we have different answers. We still have a possibility for one right and two wrong, or two right and one wrong. So now we have to argue some more. That the reason that part one is bad is that this is more than 2,598,960, which we calculated before, was all the poker hands. So now the problem is, what's wrong with this logic? Why does this become bad? Well, let's go through a scenario. I have my 13 clubs. I choose one. Which one did I happen to get this time? Just pick one. The two? Okay, so I happen to get the two of clubs. Nice. I put the other cards back in the deck, and then what did I get next? Of the 51, tell me a number. 3 of spades. Okay, and then the ace of spades. Okay. King of hearts. And finally, the 7 of clubs. That's one possibility, right? That would be one of the ones that I counted in that 3 million. Don't worry, I'm not going to list out all 3 million. Okay? No, just 52 cards. Just jokers in class. Second, what could I have chosen instead of the 2 of clubs to at first? Would it be possible that I could have chosen the 7 of clubs to start? Right? And then could I have chosen the 3 of spades to go with it? The ace of spades to go with it? The king of hearts to go with it? And then the 2 of clubs, because it's now in the deck. In this method, those would have been counted separately. But they're the same. Okay? As soon as you introduce multiplication, which we have also over here in our cases, you create an order of something happening first and something happening second. Now, sometimes that order doesn't matter. It didn't matter in sales pitch number 3 because the first thing I chose were clubs. The second thing I chose were not clubs. So we never had a problem. But you do have a problem because in this one, there's overlap. You could have chosen the 2 of clubs in this part, or you could have chosen the 2 of clubs in that part, and then you're going to count some things too many times. And that's going to be a problem. So that's the reason that we got a number that was way too big. But the other hard part about a combinations unit, and what this example shows, is your mind might come up with something that seems logical. How do you get past the idea of, is it logical or is it not? So one of the things we want to be careful of with combinations question, if you're counting things separately, you don't want to have overlap where something could be chosen in one part and then there's an opportunity for it to be chosen again in another part. So when we did our girls and boys question, there's no overlap here because we chose the boys first and then we chose the girls. But if you chose one boy and then chose 4 other people after that, there would be some overlap because you added the boys into the second part. So that's one part where you want to be careful with. Okay, so we're going to find a blank piece of paper in our notes. I think there would be one. Let's see. There's one on page 734. And for those of you that like poker, we'll go a little bit into figuring out poker hands. What are the chances of getting certain things in poker hands? The first hand that I showed you had nothing the same. It was the lowest kind of poker hand. It'd be worth next to nothing. A common poker hand is where you have one pair. So if you got one pair, I'll give you an example. It could be like getting a pair of eights, and then the other three numbers are all different. So that's what a pair means in poker. You get two cards that are the same number, and the other three are different. So how do we count this? Well, we'll do a couple of examples, and then after seeing a couple of examples, I'll talk about the strategies that I've used and some of the things that you can use to figure them out. If I tell you the strategies right now, it's going to be too confusing. So we'll sort of talk about them, revisit the strategies as we go. So what happens here to get a pair of eights? I have 13 different kinds of cards in the deck, right? Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need to choose one of those 13 to be my pair. Because I could have, to have a pair, it could be a pair of eights, it could be a pair of fives, it could be a pair of kings, it could be a pair of aces. There's 13 different numbers to choose which one I'm going to have my pair. Then, once I've decided on eights, how many eights are there in the deck? There's 4 of them. Clubs, spades, diamonds, and hearts. I need to figure out which 2 eights I pick in particular. So those two numbers together are going to figure out all the different pairs possible in a whole deck. Because first you choose which number, and then once you've chosen the number, there's 4 of that card, you need to choose specifically which 2 eights you're going to pick. Then after choosing the pair, you need to have 3 different cards left over. And you're going to do that by saying there's 12 numbers left. I need to choose which 3 are going to be my single numbers. So I choose the 3, the 5, and the 7. Then after choosing which numbers, you say, well, there's 4 3s. Which 3 am I going to choose? 4, choose 1. There's 4 5s. Which 5 am I going to choose? 4, choose 1. Which 7? 4, choose 1. And this altogether will be 3 single cards. We're going to do 2 pairs next. And then we'll talk a little bit about the strategy. So an example of 2 pairs could be like getting 2 5s, 2 queens, and an 8. That would be an example of getting 2 pairs in poker. So first of all, for our 2 pairs, we need to know which numbers we're going to pick. So there's 13 numbers in the deck. We need to choose 2 of them because we have 2 pairs. If you chose the 5s and the queens, how many 5s are there in the deck? There's 4 5s. You have to decide which 2 you're going to pick. And there's 4 queens in the deck, so you need to choose which 2 you're going to pick. And this all together will give you 2 pairs. Now you need to choose a single card. How many numbers are left? You could do this separately. There's 11 numbers left. You need to choose one of them. So you choose the 8s. And then there's 4 8s. You need to choose one of them. This will give you a single card. You could have also done that together. Because you're just choosing one single card, there's 44 cards left, because after taking out all the 5s and all the queens, that would take out 8 cards from 52, leaving you with 44 left. And since you're just choosing one of them, that could have been done all by itself. But now that we've done 2 of these, I want to talk a little bit about the strategies that I used to figure these out. First of all, what I want you to notice is that I'm going to underline things here. In the first example, underlined in green, there was 1 pair, but there was 3 single cards. In the second example, there was 2 pairs and 1 single card. Those are different sizes of groupings. A pair is 2 cards, single cards are 1 card. So whenever we're choosing cards of the same size, they have to be chosen at the same time. Otherwise, you could create order. So for example, in the first example, see how I did 12 choose 3 and chose all 3 numbers at the same time. But I didn't start off by saying 13 choose 4. Because I don't want to choose all 4 numbers. I want to choose in particular which one's going to be my pair and which ones are going to be my singles. So we choose numbers of the same size at the same time. So in the second example, I had 2 groups of 2. So I chose the 5 and the queen at the same time. 13 choose 2. Because if you did 13 choose 1 for your first pair and then 12 choose 1 for your second pair, it would count 5s and queens different than queens and 5s. But those are the same hand in the end. It's okay to count 5s and 8s with a queen different than 5s and queens with an 8, because those are different, because once you'd have 2 queens and once you'd have 2 8s. So anytime that we're choosing types of numbers that are the same size, we choose them at the same time. That's why there's a 13 choose 1 and a 12 choose 3. That's why there's a 13 choose 2 and an 11 choose 1. Then after you've chosen the kind or the number that you're going to pick, you have to think, well, there's 4 cards of each of those numbers in the deck. So for my queens, 4 choose 2. For my 5s, 4 choose 2. For each of my single cards, 4 choose 1, 4 choose 1, 4 choose 1. And you go from there to figure things out. So if you wanted to do three of a kind, an example of 3 of a kind is 3 kings, an ace, and a 5. You'll get, if we do our kings first, there's 13 different kinds of numbers. You choose one of them to be your 3 of a kind. Then of the 4 kings, you choose which 3. That will choose your 3 of a kind. Then your 2 single cards, now there's 12 numbers left. You need to choose 2 of them. Choose your aces, which ace. Choose your 5s, which 5. And that will count your 2 single cards. And as we're counting these things, if you actually do the calculations and multiply them out, you're going to find that our numbers are going down, because 3 of a kind is considered a better hand than 2 of a kind. And 2 pairs is a better hand than 1 pair. And so the fact that there's less of something means that you have a less chance of getting that kind of hand when you play, and so that's what makes it a better hand. How many have heard of full house in poker? What does full house mean? You have 3 of a kind, so you could have 3 2s, and the other 2 are a pair, so 3 2s and 2 5s. So we choose which hand is going to be our 3 of a kind. And then we choose which one is going to be a pair. And that's actually easier to calculate than some of the other ones we've done. So we choose the numbers separately because they're of different sizes. So 3 5s and 2 2s is different than 3 2s and 2 5s. So you could use this similar strategy to figure out 4 of a kind. This strategy, and we're not going to go into the strategies of figuring out flushes or straights. They're not super hard, but they're not necessarily that easy. Royal flushes are easy. There's only 4 of them. 1 in clubs, 1 in spades, 1 in hearts, 1 in diamonds. So that's what makes them so super rare. But this gives you a sense of how you would calculate the possibilities for different poker hands. And then if you divide these by the 2.6 million of all the total hands, you could find your chances of getting dealt that. Right? We could do my first one that I got, all 5 different cards. You would start with 13, choose 5. Then 4, choose 1, 4, choose 1, 4, choose 1, 4, choose 1, 4, choose 1. And you could figure out what are your chances of getting all 5 different. And if you look at the numbers, you actually find out, oh, which things are actually really close to about the same chances, and which are the ones that are a big jump difference.